So hello and welcome in this Midas NFX webinar, FEA Foundations, how to check any mechanical product design with linear static analysis. So I am Stepien and I am together with Piotr Stepien.
Yes, welcome everyone.
So in today's webinar I will present a lot of very interesting topic. I made special presentation just for this webinar to present everything in detail, and you will have some things that we never explained in the previous webinars. So this is the table of content for today's session. So first I talk about why linear static is very useful to check the product design. I'll then talk about some assumptions that you should know when you're using linear static analysis. I will show you some very simple theory, something that everyone should know about linear static analysis. And I talk about constraints, loads. I talk about contacts and the traps to avoid when you're using contacts. I'll show you how to go for a more advanced analysis than linear static. And finally, Piotr will take the screen to show you some interesting examples that he chose just for you. So let's start. And by the way, if you have any question during the webinar, just write it in the chat section and we will answer them at the end of the webinar. So the first thing I would like to talk about is when do you actually need simulation when you're doing product design. So this is very interesting topic because this is something every engineer and product designer should know, because when do you actually use simulation? So there are three, let's say, main ways where you will actually need simulation in a product. So the first is before the product is actually created, simulation will help you to find and design the right product. Secondly, after the product is designed, simulation will help you to check your design to be sure that it's not failing. And finally, after the product is released and sold to your clients, you may have problems, and FEA will be here to check what is the reason. So I'll present very briefly this topic more in details because it's very interesting and I am sure you will learn a lot of things. So first of all, simulation in the product conception. So when designing a new product, you always have to select the best option from a range of possible choices. So and if you're the designer, you don't really know which one is better. Let's say you know it from experience. If you have a lot of experience, you know this kind of product is working, this kind of design maybe not, but it's very difficult to describe. And actually this is something simulation can help you to do, because it's very important to find the optimum design, the best design. Why? Because actually it will not cost more to produce or to design. It might cost even less, and everyone will be happier because product will be more resistant and it will sell better. So that's why. So as I was searching for the optimal design is not easy and it takes time. So we generally choose something close to what we think is optimal, but actually what is happening a lot is that we simply just enhance an existing design. So we're taking something that exists and we're saying, oh, I'm adding some mass here, I'm adding some part here. Oh, now this is new design. Actually, this is just a bit improved of what exists, but there are so many products that could be created and doesn't exist because simply people never thought about it. So if you had a way to help you to conceive products that no one ever thought about, that would be a huge leap for your company, wouldn't it be? So how actually can you search for better design in a systematic and practical and also affordable way? Because it's easy to say, oh, you have to be creative. You're a designer, so just think about the solution. Actually, there are things that you can do if you're not so creative either. So you can use FEA simulation and tools that I call optimization. So it's called topology optimization, for example. And as well, you can use the linear static that I will present today to check the product. So I will not talk about topology optimization in this webinar because this is not the topic. I will just tell you that this is a very useful tool to make the right choice and provide optimal design for your model. So if you are interested by this topic, you can go on YouTube and search for topology optimization for better design with minus NFX, and you will find this webinar that I did previously, which is very interesting. And as you see, a lot of people watch it. So you can watch this webinar. Now, how do you use simulation to check the product design, and why do you actually need simulation to do that? Well, actually designing a product is not a straightforward process. It's not something that just comes to your mind on a paper and in one blow you will get a product. Because there's a lot of things to think. Product may be used like that, it may be used like this, and you cannot think about all the cases, all the possibilities that people will use your product. So because of that, you have to design it incrementally. You have first to do one design, then you have to check, let's say, a number of cases that it may fail. Then if it fails, you just redesign it. So you add some part here, you add some mass, you redesign it. And this is what I call trial error process. You're basically wanting to find the failure mode of your product to make it better, so it will not fail like that. So this is why I call that trial error. And because of the design should be checked at each step, we want to be sure that we have the right tool to check this design every time. Because if you have to do a lot of iterations, you need some tool which is very easy to run again the design by doing a small modification and just get new results. And you see here on the example on the right that I have like 4 design modifications, but in an actual product you may have much more than that. You may have thousands iterations before getting a product, because such products are very expensive and the companies are they are living because they are selling this product. So if you get a failure that will get millions of dollars of problems, that's something that company definitely wants to avoid. So that's why simulation is a very useful tool in this kind of situation. Now the third case you use simulation is when your product actually fails, because let's not deceive ourselves by telling us that design never fails. That's not true. There's a lot of products that fails, and your product could fail also. Even if you think you have the best design in the world, it may happen that someday one client will use it in the wrong way and it will just break. So you have, when it happens, because you didn't forecast this, you have to actually know what is the cause to improve the design again. And that's why you use simulation. And I can tell you, in most of the cases, people are using simulation in this case. When the product is failing, they just call a consultant and they ask him, I want to know why my product failed. We have no experience in simulation, but the product fails, so we have to redesign it. How should we do? And then you have to be able to analyze this model and tell him, oh, it failed because there was not enough stiffness in this area, the stress in this area is too high or something like that. And in this slide you see that there's a video So I strongly advise you to watch this video. It's a short story about the failure of a pressure vessel, and the video is called Failing Through the Cracks. It's like, I think, 8 minutes video, so it's very short but very interesting, and it shows you exactly this kind of case that someone designed a pressure vessel and then it after a few years it just exploded and it created a big problem, you know, and people were looking why it failed, and they found that because there was some problem in the design because of that, and they explain you because of that. A very interesting video, so you can go on YouTube and just search Failing Through the Cracks and then you will find this video. Okay, now let's talk about why linear static helps tremendously to check the product design. And I want to emphasize this slide because a lot of people don't know these three things which are so obvious when you are using linear static. So the first thing is linear static is the most simple simulation you can do. So you have to know that because there's a lot more analysis types behind that you use in special cases, but linear static is really, let's say, the basis. If you say I'm doing finite element simulation most of the time, it means that you're doing linear static. So from what I know, like 90% of the analysis are done in linear static. So then why do we use linear static? Because generally people who do product design, they just want to know one thing. They want to know, will my design fail? You know, will the stress be too high, and will there be a problem in my design? And the third thing is that they want to know if it is over-dimensioned, because of course your product can be very strong, and it can be as strong as you want if you put enough steel. You know, you can think like that. And if you're producing only one part, that's okay. You know, you're doing that in your house. You can build whatever you want. But think about the company who has to build millions of the same part. You know, 1% of the material you save on that is maybe millions of dollars. So you really have to. It shouldn't be over-dimensioned, and it shouldn't fail, of course. So those are two things that say that you check with linear static. Now, linear static will help you to avoid failure by preventing stress concentration, and also retain uniform stress distribution and eliminate the unnecessary parts and further straighten necessary parts in order to produce an optimum design. So this is basically a more complex way to say all the things that I just told you previously. So that's for the engineers who like very complex sentences. So now let me talk you very simply again. What is linear static? Why is it called linear static analysis? And so I just took these three words, linear static analysis. Let's look at the first word, linear. So it's called linear because the relationship between the load applied to an object and the response of the object, which means displacement stress, is linear. So you see I have a curve, so this is basically the force is proportional to the displacement. That's why it's called linear. It's static because the applied load does not vary based on the time, and you are ignoring the inertial and damping forces. So what does it mean? It means basically that you consider that when you apply the load in linear static, the load is applied so slowly that the model doesn't feel the moment when you apply the load, and you can consider that the load is always applied on the model uniformly and it doesn't depend on the time. So you are ignoring, let's say, the moment where you apply the load. So this is why it's called static. So it actually doesn't move. That's the thing. It's static. Now, be careful. So that's why I put a big warning. There are some assumptions ahead that you have to know. Linear static only works if you can verify the assumptions. And this is something that I have to tell several times, because a lot of people who are not careful about that, they're just thinking, oh, finite element analysis is like that. So they don't know actually that there are more than analysis types that linear static. They just do like that, and they apply the same method to every type of analysis. But be careful, that's not true. It's only valid when the assumptions are validated. So what are the main assumptions? So you have two types of assumptions. So you have the assumptions because of the linearity. So three main assumptions. The first is that your material behaves within the elastic region, following the Hooke's law. So you see on the right you have the curve. So this is, let's say, general curve for a steel material, and you always suppose that you are in the elastic region here on the left, which is considered as linear. So you have linear relation between the stress and the displacement. So deformation must be small. So this is the second thing. The deformation must be very small enough to ignore the changes in the structural stiffness due to the deformation. So it basically comes from the first relation as well, because as you see on the curve, if you are in the linear elastic region, your displacement has to stay small. Otherwise, if it's bigger, you go off this zone. But it also means other things. And actually, Hooke's law is not linear if, let's say, you don't consider the small deformation. So yeah, it's more complex and it's not linear. So this is why these assumptions allow the fact that you can consider the linearity. The third condition is boundary condition must not change. So while a load is being applied at a certain position, your structural deformation is occurring, but you cannot say that, oh, because there is deformation, so my load is changing the direction. No. In linear static, your load stays always the same direction. That's assumption. The second, let's say, set of assumptions is the assumptions because of the time dependency, because as I was telling, this is static, so loads do not vary in time. So here on the right you have a sinusoidal force loading, so you cannot consider this type of loading in linear static. The second is that you ignore the inertial and damping forces. So for example, acceleration, deceleration, you can think about Coriolis maybe. So all these forces are ignored in linear static. Now, I told you at the beginning that I will tell you a very simple formula that tells about the linear static, and this is it. This is the Hooke's law. So if you consider a simple spring, you can express the relation between the force and the displacement like that, F equal K delta. And this is basically what we associate a linear static analysis with a spring. So it means that this is only in one dimension. So in one dimension you have a relation like that. So the K is a constant and the F is proportional to the displacement. If you are in three-dimensional, the F becomes a vector and the delta becomes also a vector, and the K becomes a matrix with 9 components. So this is still the same concept. So the K is the stiffness. So it means that your model in linear static will react like a spring. When you apply a force of 1 kilogram and you have a deformation of 1 millimeter, it will be proportional. So if you have 10 kilogram, you increase the force, your displacement will be proportional of 10 millimeter. This is very important to understand that. And from what you see here, you can think, oh, what if I increase the force like 100 kilograms? Will I have 100 millimeter of displacement? this is where you have to be careful, because if you have that, you're not verifying the assumptions that you are in the small displacement. And that's where it's wrong. So in this case, you cannot use this formula. Now let's talk about how to constrain and load your model properly. So this is very basic, because a lot of people asked us, oh, what is a constraint? So at the beginning we were thinking, oh, that's so obvious. But as some people don't, understand fully, I decided to present it in a very easy way. So constraints describe when the model is fixed and how is it fixed, let's say. And loads describe the force or the pressure which is applied externally to the model that causes the mechanical deformation and stresses. So you have a small picture on the right. So probably if you're an engineer, you're thinking like me, oh, this guy is not static, he will probably move with such a big load. And that's right, but that's what only, to give you a small illustration that, you have the load, the constraint is where the guy is blocked. So let's suppose he's not moving for this case. But by the way, I'm not saying I'm doing linear static in this slide. So that's another thing. Okay, you have different type of constraints, and to understand that you have to know a very simple concept which is called the degree of freedom. So basically the degree of freedom describes how a model is free to move in a 3D space. So you know that model can move in 3 directions because we have 3 spatial directions, and it can rotate around the 3 axes, the 3 main axes. So we have 6 degrees of freedom when the model is not constrained at all. So the maximum for one part is 6 degrees of freedom. So when the model is constrained in one position, what you do is that you are actually removing some degrees of freedom. So for example, you have, let's say, 3 main type of constraints. We have what is called the fixed constraint, which is removing the 6 degrees of freedom. You have the pinned constraint, which is removing 3 degrees of freedom in translation only, so it allows the rotation. And you have a no rotation constraint, which is basically the contrary of the pinned constraint. And of course, you can constrain as you want any direction of the model. So you can say, oh, this face will be constrained only in X direction, and it will not rotate in X direction. So all these things are the different ways to constrain the model. But how do you actually constrain properly your model? Because this is something a lot of people are wondering. How do you know the correct way to constrain your model? And here I have to tell you something. There is no straightforward way for any model, which means that you will have to find your own strategy for each model. And how do you do that? Here's a way. I wrote you in 4 steps. The first thing is you have to visualize how your physical model can move in the reality in translation and rotation. So you see here on the left, this is the real product in action. So how is it intended to be used? Now let's say it's fixed and the woman is sat on this position. So you can say, oh, the model will be fixed here like that. You will apply some loads there and there. And this is, let's say, your assumptions that the constraint will be like that. So you have to ask you these questions. First, visualize your physical model. How is it fixed? How is it constrained? Then which part is fixed? Think about it. Which surface of your model cannot move, and in which direction? Is it really fixed, or is it pinned, or is it one specific direction which cannot move but it can rotate in another? Where is the model fixed exactly? Now all these things, and this is only 4 questions, but you can ask yourself much more questions. But by asking yourself those questions and making some assumptions about how your model will be constrained, you can find a way to do that. But again, I have to warn you, that you have to be careful with the assumptions because they may be wrong. So we always have to keep in mind the possibility that we are wrong somewhere. So you have to check the assumptions that you're doing by simply analyzing the model and seeing if it makes sense. You have to look at the result and think, oh, does the result make sense for me? And in some cases it's obvious, but in other cases it's not. So you have to, do some trial errors. So basically this is what I call the improvement circle. So you have to ask yourself, you have to imagine how it should be constrained, you have to plan how you should constrain it, then you have to do it, to do the test, and if it's not satisfactory you have to improve, and you have to do that over and over again until you get something that works. That's how real engineers are working. Now let's talk quickly about the contacts, because I told you that I will give you also some very simple description about the contacts. So yesterday actually Piotr told me that contacts are another way to constrain a model, and I thought that was a very good way to describe what is a contact. So I'm just telling you that today, that when you have assembly of parts, you have to think that one part is constrained relatively to another. So you cannot use the basic normal constraints that you have, like fixed, in every time, because you don't know what is the exact relation between two parts. So you have to use another type of constraint, and this can be called contact. So contact is some kind of constraint between two parts when you don't exactly know what kind of constraint it is. And you can have friction force. Okay, Piotr's telling me that I'm telling bullshit, but he will explain you later maybe. Okay, let's pass on that then. So how do contact actually work? So the thing is that in a FEA model, your element, you know that the model is divided in a lot of small elements, so and nodes, and the purpose of the element is actually to connect the nodes together. So you need to have this way, but when you have two parts in the assembly, you have no elements between the two parts. So how do you connect the nodes between the two parts? So this is also done through the contact. So this is the way I understand it from the beginning, is that when you have no element to connect two nodes between two parts, you're just using contact, and you will create a relation between the nodes of the two parts together. Now I'll tell you that I will tell you a few traps. There are much more, but this is a starting point if you need to assign contacts in your model. So the first thing you have to know is that you have to use the proper type of contact. There are different types of contacts. Especially there are linear contacts and there are non-linear contacts. The second thing is you have to consider or not the friction and the sliding, for example, and also your contact parameters. Contact parameters can have a big impact on your analysis, and you have to do some tests basically which parameter is working well, but you have some chance because in Midas and FX it's quite straightforward to do that relatively to other software. The third thing is that the contact surface and the elements in contact should be good enough to transmit the nodal data. So in some cases when your model is very complex, be sure that the contact surface is meshed sufficiently small and well enough that the contact will be transmitted correctly. And the fourth thing is that you can sometimes simply instead of using contact, you can merge the nodes together. You have this possibility, you have to know it, that you don't have to use contact in every time. In some models it makes sense to merge the node because you will get more accurate results and faster, because the software will not calculate the contact. it will simply tell the software that the nodes are merged together, so it will consider it as one part. Now, the question that maybe a lot of people in today's session have is, how do I go to a more complex analysis? Because you told me that linear static cannot be always used. You have some assumptions and everything. So how do you do when you don't verify the assumptions? Well, actually, a lot of more advanced analysis exists, and you have to know it. So in order to fit your model to the, in order to analyze properly the model, you have to know what are the assumptions, if they are verified or not. And if you check and you have large deformation, for example, then you know that you have to use nonlinear analysis. Or if you have nonlinear material model, you know that you may have plastic deformation, and then you have to go in the nonlinear analysis. So you have different type of analysis. You have nonlinear static, linear, nonlinear dynamic, thermal, optimization, etc. So I will not discuss about that too much today because this is not the point. But if you're interested by that, you can go on MIDAS-NFX website, and we have a section called Analysis Capabilities. And as MIDAS-NFX can do almost all analysis that you can imagine, we made some description for each of them, and we have some small, videos showing how it works. So you can go here and look at to understand each of that. And the second way you can do is simply go on YouTube and search MIDAS-NFX plus the thing you want to know, and you will find immediately like some video tutorial. And if there is no tutorial, just tell me, and maybe I will make one for you if you're lucky. Okay. Now we go to the second part of the webinar. So Piotr will take the mic, and he will present you. His case study about linear static.
Okay, thank you, Cyprian. This is Piotr speaking. And today, as you see, we will analyze a very simple assembly using linear static solver, or let's say linear static module. And the presented model represents widely used in industry universal joint, which is also known as Cardano joint or Cardano shaft. So as you see, our assembly consists of 3 solid parts, and main objective for the calculation will be the estimation of the strength of the U-joint cross, because we know that this is the weakest part of our assembly. So let's switch now to the software. So as you see, the geometry of the assembly has been imported. So one workflow step is already behind us. So let's go to the next step, and let's specify material data. So to do that, I'm clicking on the material branch, I'm selecting material model, and depending on the available data, we can use predefined definitions using the database, or we can specify those parameters manually. So as Cyprian said before, we are in a linear range, so for our model, only two structural parameters are required to define. And this is happen because of the assumption that there is no gravity acting on my model. So if we take a look on this part of material card, we have structural parameters, so we have to provide input for elastic modulus and Poisson's ratio only. So we can skip the mass. So this is why I will erase this data, and let's leave those input because it's good. So my material will refer to the steel. But if we click on this database flyout menu, you see that we have an access for other materials like aluminum alloys. We can define some plastics, everything in a linear range, because our database refers only to the linear range. So for example, for nonlinear materials, you have to provide data on your own. So this database can be imported from external file, can be edited, but this is not the topic for today. So I'm selecting this material, and for the calculation of factor of safety, let's specify the limit, like 230 megapascals. So this is plasticity limit, that's the value for that. Okay, so now I'm clicking on OK. And the next step will be related with the property of used element. So from the geometry, we know that solid element will be used, and this is why I'm going to this property branch and I will create 3D property. So today we are not talking about the element types and the theory behind that. So we are doing the model using the solids, and this property basically is giving the right material attribute to the solid element. So this is why from this menu you can add the proper material, the proper definition that will refer to your part. So let's click on OK. And we have it. So the next step, let's move to the next step and let's create the mesh. So a mesh will be created automatically. So to do that, I'm clicking on the generate, and I will select all of the parts. So I'm selecting part to the left, cross, and the third part. As the size, I'm specifying the size of the particular element, and this will be 10 millimeters. And I will use high-speed tetramesher. This is the best, the fastest, not the best. Actually, this is the fastest way to create mesh for your assembly. So let's click on this, and let's observe how the mesher is doing his job. So as you see, all of 3 parts are being meshed simultaneously. And this is possible because architecture of our system is 64-bit, and the meshing algorithm is also built on this architecture, and whole process takes a few seconds only. So okay, done. And let's click on the static tab, and let's think about boundary conditions, and let's start to think about boundary conditions. So as you remember, Stepien was telling that this is the most important step during your workflow, and he has obviously right, because the application of boundary condition is very sensitive topic. It's very tricky subject, and basically it's based on pure engineering judgment, your engineering skill and common sense. So no university, no consultant and book can teach you the right constraining process. This is something you can get from practical and field experience, and this means that you have to think all the time about your structure and how the structure is subjected to the forces and how the structure will respond to these forces, and you have to make some comparisons with the real world if it's possible. So for that, it's good to have some additional data like displacement plots or some other graphs, some strain gauges results to perform this comparison. So if your model does not or let's say it's not behaving correctly, then obviously you have to provide some modifications to your boundary conditions, and it will be much more easier when you start to talk about this topic with the more advanced, more well-educated engineers, more experienced engineers, because the process of getting this knowledge is quite long, and as Cyprian said, there is a trial and error method, in short, and this method actually is the best teacher. But let's back to this model, and let's assign the boundary condition. So I will rotate my model in the proper view, and I will assign the boundary conditions on the front at the front face of the inner side of the shaft. I hope this makes sense what I said. So let's go to the constraint, and let's assign pinned constraint condition. So today we are not talking what is fixed, what is pinned, and we are not talking actually what options we have in regard to the constraints. We made several webinars about that, but today we want to show some basic knowledge for the beginners especially. So So I'm selecting the pint. This button is related with the degree of freedom of particular element. So so I will back to this in few seconds. So let's go to the type. Let's select the face. Using the selection toolbar, I'm changing the method for the selection, and I'm clicking on the circular tool. And having that, I'm simply selecting inner faces. So as you see, the inner faces from the shot has been selected. So now I'm unclicking this frontal face. I don't want to create a constraint there, and I have to unselect the rest of the faces which were being selected, but it was not my intent to do that. So I'm clicking on the selection toolbar, and using unselecting mode, I'm unchecking all of them. So let's click on OK, and that's the visualization of the constraints. But before we move on, let's take a quick view on the second model, because we are receiving a lot of queries and a lot of questions which are related with this simple error. So many people have this error, especially at the beginning of the FEA adventure. So, and the error has got a number, is 2007, and the full message says factorization failed due to singularity at translation X of the node, and we have some information about the number of the node. So the first part of this error is actually not important for the moment, like this factorization failed due to the singularity. So this refers simply to the mathematics, to the matrix algebra, and it says that your stiffness matrix is singular, but this is not the point to talk about this theoretical background. Right now it's important to focus on the second aspect and try to guess how to fix this problem, because 90% of your issues with linear static comes from bad or poorly applied boundary condition. So that's the biggest problem. So let's take a look on this model. As you see, this is a simple box, and this box has been subjected to the pressure. So let me analyze quickly. So I'm solving this, and as you see, that we have the same factorization problem, or let's say we have the same error. How to fix that? So basically, if we back to this solid element, again, it's related to the degree of freedom. So Cyprian was telling you about degree of freedom in terms of the positioning of your part in the space. But and that's right. But the second aspect about degree of freedom refers to the element itself and to the node. So before your modeling, you have to go to the manual of your software, and you have to study a bit about your elements and degree of freedom of your elements. How many degrees of freedom are available from each particular element. So for example, solid element has got only 3 degrees of freedoms, and you have to constrain your models, your faces, based on that. So right now software is telling us that translation along x axis. So you can take a look on the global cross, on the global Cartesian system. So x-axis is here, so you have to fix this somehow. So I'm going to the boundary condition. I'm clicking on user defined, and I'm selecting the face. So let's assign this boundary condition on the bottom face, and let's check this Tx degree of freedom. So now I'm clicking on OK, and let's solve it again. So what we have another error message, but this time the translation is the missing degree of freedom lies on Y direction, excuse me. So again, I'm going to the boundary condition. I'm clicking on the plus. I'm clicking on the edit, and this time I will check the rest of the degrees of freedom, because I have to fix this on y and zeta direction because the force is acting on this direction, so it's obvious that I have to check that. So I'm clicking this and I'm expecting that my model will be fixed correctly, and as you see, there is no warning, there is no issue with my model. So this is why the constraining is important, for example. And let's back to our model. So for the moment, I defined the constraints, and the next step is related with the loading. So as you see, I will apply the load to the right part, and as we see, the bolts are omitted in my model, so I have only holes, and I will use the geometry to assign the moment which will act on my assembly. So once again, I'm going to click on remote load. From this dialog box, I'm clicking on loading location. I'm selecting on I'm choosing the face as the type for my entity to apply, and I have to change the mode for the selection. So as you see now, I'm selecting some faces from the holes. So I'm not selecting all the faces from the holes, but I'm choosing only few of them, and using this command, which is called select neighboring edges or surfaces, I will select all of them very quickly. So all of them are selected right now. And let's assign some moment. So the moment will act on x-axis, and the value will be 1 to the power of 7 Newton or millimeters. And let's click on OK. So this is how I will assign the moment using the geometry, because of course I can do that manually, but for this operation I have to do much more steps. So right now my model has been constrained and loaded, and there is one step to do. Because there is an assembly, I have to create some relationship between the parts, and this is what Cyprian was saying, that we have to use the contacts. So we were always talking about the contacts, and we were explaining this feature like contacts are very important for the assembly, because they are required to create some kind of connection between the parts. But another way of understanding of the contacts is, as we say, we have to think about them as some additional form of constraints, because actually the contact is not the constraint, but it's creating some relationship between the contacting pairs, and because of that we can create some behavior between contacting pairs, like the parts, the faces of the parts can move relatively to themselves, they can be welded, they can be fixed, and based on this condition we can create some kind of temporary constraint, because if we consider contact between the two spheres, and this is what Cyprian wanted to tell you, that we can create some kind of constraint. I would like to explain that. So if you imagine that you have two spheres and you want to perform simple Hertz experiment, there is no constraint between those two parts at the contacting point, but we are looking for the reaction between those two parts, and this is why we have to use contact, which will describe proper behavior between those two parts. So this is why we are using the contact and the constraint. Let's say the kind of constraint will be created between them. So this is how you can start to think about that. So I'm expecting all of you have some comments about the way of the thinking that we are talking about at this moment. But I hope most of you will agree with that this is good assumption and good way of thinking before your modeling. And actually, if you go deeper with your modeling experience, you will understand the role of the contacts more detailed, but this is absolutely the starting point if you don't have any knowledge about contacts, and if you don't know exactly anything about the methods. So you have to start somehow, and that's the good way. Okay, so let's assign some contacts quickly. So I'm going to the contact. As you see, this is my routine. I'm working using the modeling tree. So I'm clicking on the add, and from this contact per automatic contact creation tab, I will create a contact which is called bidirectional sliding. So what is that? This will create welded or glued relationship between the contacting parts with some relative movement between them. So the touching faces will get the possibility to slide relatively to themselves. And to create that, I will use the geometry, and let's select all of the parts, and let's click on OK. So I'm expecting that some contacting pairs has been founded. So if we click on the part, you see that the system found a relationship between the cross and related shafts. So now the model is done. So the next step is to go to the analysis case and to send our model to the solver. So right now I'm going to edit. I would like to show you how the analysis case manager works and looks like. So basically it looks like you see, and from this subcase setting you can manage your loading cases, you can manage your boundary conditions. I haven't said this yet, but one of the feature of the linear static is superpositioning. So you can create combined load case, or you can create many subcases and make some combination of many scenarios. So this is the one of the feature of that. So you can do this from this place. And if you want to calculate much more than default. I mean, if you are looking for the inner forces in your elements, you can check these options, and the solver will calculate much more data rather than default. So okay, let's click on OK. And right now let's switch to the model which has been calculated. So I would like to show you the results for calculated model. So this is the result of the nodal displacement. So if we go to this analysis tab, to the results tab, sorry for that, we can display our model in many modes. So I can display the model with the edges, I can omit the edges, I can display the model as deformed, and I have also a place where I can set up the scale of the deformation. So if I click also on the play, we can see the animation, how our model is responding to the subjected load, to the applied load. So we have it, but there is one more thing that I would like to show you. So as you see, as default, only 3 output vectors has been loaded. So as default, we can display the result for the total translation. We can display result for solid von Mises, and there is something which is called solid stress safety factor. So if we double click on this, we can display our model, and we can display what is actual the safety factor. But this way is not convenient, and many of you are asking us how to display this in more efficient way, more affordable way for the designers. So let me show you how to do that. That's my way, but I hope you will like it as well. So basically I'm going to the legend, and there is the first thing that I'm going to do is select the legend, and we have an option which is called number of bands. This means that this stands for the number of the levels. So this, as you see, we have 12 levels for our contour map, and I will change that to 2 simply. I would like to get the information which part has got sufficient factor of safety, which part has no satisfactory factor of safety, and I would want to see this somehow. So now I'm going to the model and I'm unchecking all of the parts. So as you see, I'm looking for the factor of safety for this U-joint cross. And because we are using the FEA method, sometimes we can obtain peak stresses and the places where the peak values are telling us that there is a stress concentration, but not every place is the right one, so we have to make some judgment on the model as well. And we have to learn how to display some contour maps in reasonable way. So now I changed the number of bands, and right now what we have to do is to change the values for my legend. So I would like to display factor of safety which values are varying from 0 to 2, for example. So this is my design requirement, so let's display that. So as you see, from this simple change, now I know that at these areas my safety factor is below 0 and 1, and the rest of the model is very safe. So I have to think how to overcome my problem at this position, at this place. Okay, so this is all what I wanted to tell you today, and there some couple of slides left just to make some summary. So what did we learn today is about linear static analysis is that this type of analysis is the one of the most common types of the analysis. Why? It's very efficient. It's computationally less expensive, and it's always converging. This is the most important fact, but it's always converging when? Only then when your constraining works properly. This is why this is important. So all the time you have to think about your constraint from the physical aspect, from the real world aspect, this is what I want to tell you, and from the numerical world, which means you have to think about your elements, and you have to know a bit about the methods which are used for your code. Let's say like that. So linear static is also a fundamental analysis type, which means the results from linear static are very valuable according to the moving to the next more advanced analysis. So linear analysis can tell you, like I show you, for example, with this factor of safety, we have seen that some places on our model they have a factor of safety less than 1, which means that plasticity limit has been reached. So this is sometimes a suggestion to go to the more advanced analysis type, like for example nonlinear. And of course there are several assumptions with respect to the linear static. So you have to always think that my model, if I want to analyze that using this type of analysis, it should keep the frames of small deflections, which means what does it mean actually? So you have to compare the deformation with the global size of your model. So the deflection should be like a couple of percent of your global size. Similar situation refers to the smaller rotations. So if you take a look on this picture, some rotations should be also very small, some small percentage of your model. So usually we are measuring this angle using the trigonometrical function, so the tangents should be almost 1, so the angle should be very, very small. We have to take into account the material properties and constant boundary conditions. So if we go to the material conditions, once again, Stepien was telling why linear static. So just to remind quickly, there are two formulas which are equivalent. To the left, we have equation which describes Hooke's law using the stress, strain, and Young modulus. So as you see, the young modulus stands for the input parameter, and I was defining that. The F, if we take a look on the equation to the right, the F stands for the load, and I was applying my moment. And this type of loading was my loading actually that I used. K means stiffness, and it comes from the material property and your mesh. So this is the resultant of that, and we are looking for the U, which is displacement, and based on that the software is calculating other output vectors like stresses, strains, and other data. So why static? Again, you have to always think about this, that its influence of time is neglected in this, and this means the acting force is constant and there is no variation in the time, and the sum of the acting forces should be zero. So if you consider the problem, all of the sum and moments should be zero. So if we are working in a Cartesian system, so along all of the axes should be zero. For the planar problem, the number of the equations is much more less. And Cyprian was also saying about the proportionality, and this terms is called many times like scalability, which means if we apply one force to our structure, the structure will respond with some kind of displacement. So if we apply something more, like proportionally more, like 10, for example, newtons, we will get the 10 times more displacement. So this is the proportionality. I was talking a bit about superpositioning, so you can make a combination of several load cases, and you can even make a combination of the analysis cases. And the third feature, which you can also get information about, that is reversibility. But this is basically related with the loading sequence. So in this analysis, loading sequence is not important. So the final state is always the same and is unaffected by the load history. So it was basically all for today's webinar. I would like to thank you for your participation. Right now I'm giving the mic to Cyprian again, so thank you very much.
Okay, thank you very much, Piotr. So I hope you enjoyed today's webinar. Now, as you see on the screen, if you're interested to try Midas NFX, you can have a 15 days trial, which is a full version of the software on our website. So you can try exactly all the functions you want with your own model. Now we'll have a few minutes to answer the questions. So if you have questions about this presentation, please just write it in the chat section and we will answer that in live. Someone is asking if the video will be on YouTube. Yes, it will be. So you will be able to see it again if it interested you, and I hope it did. So you can just search it on YouTube when it will be uploaded. Someone is asking as well, what kind of analysis should I do if the model do not respect one of the assumptions of the linear static? Well, this is what I was telling. It depends which kind of assumption is not respected, and if, for example, you have big deformation, like you mentioned it, then you may consider nonlinear static, for example. Okay. Okay, someone is asking, can I make a webinar about singularity?
From which aspect? Mathematical aspect?
From which aspect do you want to know that? Can you detail your question, Mohammed? Singularity in linear static analysis. Well, actually, it's not very difficult to understand. Maybe you can make a short video to explain what is a singularity and how you can fix this kind of problem. I think Piotr told that during the webinar, so you can watch again the video as well. But we can explain that a bit more in details. Someone is asking, what are the limits of the small deformation? How do we say that this is small and big displacements? How do we decide? That's a very good question, because actually that's a question a lot of people are asking while they understand that you have to be aware of this small displacement. Well, the things you must see first is what is the size of your model, and you have the displacement is small or big relatively to the main size of your model. So if you have a model which is a building, maybe small displacement will be 1 meter, but it really depends. So, and yeah, and as Piotr is saying, it's related also to the material. So you have to be aware of all the parameters to monitor, and you have to do some tests, and basically you can determine if you have small deformation. Generally, in a small mechanical part, if you find 1 meter of deformation, this is that there you have a problem somewhere. Okay, it seems that there's no more question for today. So thank you very much for attending. I hope you enjoyed this session, and see you next time. Goodbye.